Welcome to lesson 3.1 and 3.2. Today we're going to look at counting by weighing and atomic masses. This chapter 3, or this section, unit 3, starts by talking about atomic masses and counting by weighing, and it moves clear to something called limiting reactants. And so what we're actually looking at in this chapter is we're looking at stoichiometry. And stoichiometry is very important to chemistry, number one, because it's my favorite word, and secondly, because it allows us to relate how much reactant we use to how much product we get. And that's extremely important in industry in terms of synthesis and things like that. We're also going to look at atomic masses and moles. One of the things we start off with here is something called average atomic mass, or average mass of an object. And so we'll look at the average mass of just an everyday object. So let's think about if you had a mason jar full of pennies and you wanted to know how many pennies were in the jar and you didn't have time to count them, then if you had a balance handy, what you could do is you could get the mass of maybe 5 different pennies and figure out what the average mass of one penny is, and then you could get the mass of the whole container and divide that and figure out how many were in the container. I like to do this with a bag of candy. So what you can do with a bag of candy is you can get the mass of one piece of candy, and then you can look at the side of the package and figure out how many or how much that is supposed to be in the bag in terms of mass. Divide that total mass that's supposed to be in the bag by the mass you got of the individual candy, figure out how many candies are supposed to be in there, and then actually count them to see if they actually put the proper number of candies in there. Same kind of thing can be done with atoms, but atoms obviously are a much smaller scale. I can't just pick out one atom and put it on a scale and then figure out how many atoms are in a certain object. And so we'll learn how to use a concept called Avogadro's number later. In 1961, they set the standard for atomic mass units is carbon-12. Carbon-12 has exactly 6 protons and 6 neutrons, and they said a carbon-12 atom which has 6 protons and 6 neutrons is going to have a mass of 12 atomic mass units. We're going to go through the next couple of slides. Are going to talk about a mass spectrometer, and a mass spectrometer is a device that's used to actually determine mass. It can also give you the percentages of that particular mass that are found in a particular compound or a particular mixture. We will talk about this just so you know the instrument behind the process. It's not something that you need to understand in detail. And the next few slides are going to talk through this in words, but what you do is you pass a sample through into this chamber. What happens is electrons are knocked off, and the sample is forced to be positive ions. The positive ions go through a magnetic field, and the lighter ones are allowed to bend. They bend more than the heavier ones, and then so you can see that this particular mixture is split into 6 different masses of the compound, and that helps us determine exactly what the atomic weight is. And I mentioned that a mass spectrometer can also give you abundances, like what percent is certain atomic weights, and so that can help us determine the isotopic composition. So average atomic mass or atomic weight, that was defined by the International Union of Pure and Applied Chemistry. So anytime you say average atomic mass, you actually mean atomic weight. A lot of elements exist in nature as mixtures of isotopes, so that's why when you look at the periodic table, very seldom do you see a whole number. If you do, it's usually in parentheses. We use the abundances and the masses of the particular isotopes to calculate the average atomic mass. So in this example, notice it says there are 3 naturally occurring isotopes of carbon, carbon-12, carbon-13, and carbon-14. But also notice at the bottom of the slide that carbon-14, they do not give you an abundance of that one. That's because the abundance is so small. So we're going to determine the atomic weight of carbon based on its isotopes and the abundance of each isotope. So what you do is you plug that into basically a simple arithmetic operation. You take the percentages and you turn them into decimal form. So you basically move the decimal over two places, take that times the mass. This U here is a unit, it is not a variable. So 0.9889 times 12. And then you're going to add that to the percentage of the carbon-13 in decimal form times the mass of the carbon-13. And when you add those together, you get 12.01 AMUs. And that is the mass, the atomic weight that's listed on the periodic table for carbon-12. Here we have another isotope where we do the same thing. We take each of the percentages, turn them into decimal form, and then take them times the masses. And so let's go ahead and do that. And instead of you seeing my sloppy writing, I'll just kind of talk you through the process. And you always want to use parentheses on your calculator as often as possible. So top one, let's look at this one first. If we turn this into a percentage, we're moving the decimal over two places, so 0.0140. Take that times the atomic mass here, 0.973. We're going to add that to, and we're going to put, so we're going to say plus open parentheses 0.241 times 205.9745, close those parentheses, plus 0.2210 times 206.9759, close the parentheses. And the last one, we're going to open some parentheses, put 0.524 times 207.9766. Close those parentheses, and we come up with an average atomic mass of 207.2 AMUs. If we look at the periodic table, because it asks us to identify the element, look at the periodic table. The only element with that mass or close to that mass is lead. Same thing on this one. They do this one just a little bit differently because this says relative number of atoms. Notice these two add up to 100%. So you could do the same thing here where you move the decimal over two places. But notice what they did. They went ahead and left the decimal as is because they put that many atoms. And then they divided by 100 atoms. You'll get the same answer if you move the decimal over here, or if you just leave it this way and then divide by 100. Does that answer make sense? So we came up with 63.55 as the average atomic mass of copper. Notice here the smaller one, or the less massive one, is 62.93. The more massive one is 64.93. So the average should be somewhere in between, and 63.55 is somewhere in between those two numbers. So that's where your reality check is. On indium here, we have an atomic number of 49, so that means it has 49 protons. Its atomic mass is 114.8 grams. On this particular example, they don't give us a very specific atomic weight. You know, like before, it wasn't just 62, it was 62.93. So in that case, you're going to use the atomic weight that's given in with the element, and we'll do the best we can here. So this one requires a little bit more algebra. So let's say our indium 112 is X. So if these are the only two isotopes, that means our indium 115 must be 1 minus X. When we follow through with the math on this, what we'll do is this is basically the percent composition of each. And so just like we did before, let's take the percent composition. So X times 112, so percent composition times the mass, plus, and this one's going to be 1 minus X, so percent composition times the mass, and that's going to equal the average atomic mass, so 114.8. when I do that math out, when I run that 115 through, I actually end up with negative 3x equals negative 0.2. And so I divide both sides by negative 3, and I end up with x being 0.067. And so if you're looking at percentages, 112 is about 6.7%, and 115 is about 93.3%. Okay, I hope you can read that. It's hard to read, so that's a 115. Okay. The next slide gives us multiple choice. So remember, 112 was about 6.7, and 115 was about 93, and it wants to know the abundance respectively, so the ratio of 112 to 115. So here I've got basically 7 to about 93. So let's look at our multiple choice, and we have one that's really close. We have 6 to 94, and so that would be the correct choice on that one. And I'm sure we would get closer to 6 to 94 if we had the actual masses instead of the rounded masses. This last question asks about zinc and aluminum, and so let's look at zinc and aluminum on the periodic table. It says, in the question, it says each sample contains the same number of atoms, and it wants to know which of the following statements is true concerning the masses. So first, let's look at the masses before we go to the next slide. Aluminum's atomic weight, or average atomic mass, is basically 27. Zinc's average atomic mass is about 65. So zinc has, if I have the same number of atoms, zinc, because each atom has a mass quite greater of zinc than aluminum, then we know that there's going to be more mass there. So the mass of the zinc sample is more than twice. So if aluminum was 27 and zinc was 65, 65 is more than twice. So we're going to say A, but let's look at the rest of them. Mass of the zinc sample is more than twice, is more than the mass, but not twice as great. We know that's not correct. Mass of the aluminum sample is more than twice as great as the mass of the zinc sample. Well, aluminum is not more massive. And then also D is incorrect, and we know they're not equal. So it's just kind of like bowling balls and marshmallows. If I have 5 marshmallows, it's going to have a different mass than if I have 5 bowling balls. So I have the same number, but the mass of the bowling balls is greater. So just like zinc and aluminum, zinc has each atom has more mass than each atom of aluminum. And so if I have the same number of of atoms of each type, then the element that has the higher mass per atom is going to have a higher mass, a higher total mass. All right, so that concludes section 3, 1, and 2. Next time we're going to talk about the mole, which is the counting unit of chemistry.